Good morning, everybody. I am Wilfred Justin from Amazon Web Services, and with me is Raj Karyala. And today we are going to present a very interesting use case, bird sound classification that uses Amazon machine learning stack. We all know that artificial intelligence is ubiquitous, and from AWS perspective, literally we have hundreds of use cases across multiple verticals, but we decided to present this use case for two reasons. Number one, it is a pretty interesting use case and has technical merits because we are going to walk you through the steps on how you could use the sounds generated by birds to classify its types. Second, we are all part of public sector and we are super focused on applying technologies including deep learning and machine learning for a higher cost. That includes protecting this planet Earth, conserving nature, protecting endangered species. So if you think about protecting endangered species, it all should begin with identification. You should be able to identify the species and perhaps identify different family members within the species, and then you can tag them, track them, and protect them. So since this use case is all about classifying birds and bird types based on the sounds, we thought it would be a pretty interesting use case and it would be appealing to the audience. So let me begin my presentation with this opening remark. More machine learning happens on AWS than anywhere else. And as you could see from the slide, we have more than 10,000 customers using our machine learning stack. We have twice the more customer references than any other cloud provider. And we all know that TensorFlow is the most widely adopted framework when it comes to machine learning. But if you think about the projects that uses TensorFlow and applications that are built on TensorFlow that runs on the cloud, 85% of those applications or projects that runs on the cloud runs on AWS. And it is primarily because of two reasons. Number one, it is because of the depth and breadth of the broader AWS cloud computing platform. So beyond the basic infrastructure services like compute, network, and storage, we offer powerful higher level services that includes relational database services, that includes powerful big data services, our own machine learning stack. On top of it, we have identity and access management for fine and coarse grain authorization, and we have a bunch of security services. So customers can use this platform to ingest large volumes of data, either in real time or in batch mode. They can store the data without compromising security and privacy, and they can process the data, and perhaps they can build a data lake on top of which they can run a lot of machine learning workflows and applications. The second important reason for this is our differentiators of our machine learning stack. That's what I'm going to focus on in my short presentation. So when it comes to artificial intelligence, our goal is to put machine learning in the hands of every single developer. So you could be an expert machine learning practitioner, you could be a data scientist, or you could be an application programmer with no background on machine learning, but still you should be able to leverage our platform and build sophisticated artificial intelligence based applications pretty quickly and easily. And that's our goal. So as part of our mission, we provide our machine learning stack, and it comes in three layers. I'm going to start with the bottommost layer, and then I'm going to pivot to the top layer, and I'm going to focus on the middle layer, which is Amazon SageMaker, because that is the service that we are going to use for this particular use case. So to begin with, the bottommost layer is meant for expert machine learning practitioners. So those are the domain experts who are comfortable in choosing the algorithms and frameworks given the use case and given the problem. And not only that, they are comfortable in tweaking and optimizing the frameworks and algorithms, and also they're extremely comfortable in dealing with the infrastructure tasks associated with it. So for those machine learning experts, we offer three things from the bottommost layer. One is flexibility, second is performance, and third is cost saving. So when it comes to flexibility, unlike other cloud providers, we just decided to support multiple frameworks because we work backward from the customers. And from what we hear from our customers is that for different kind of problems and for different kind of data sets, there might be different frameworks might be optimal. So from a platform perspective, as a cloud computing platform provider, we want to support multiple frameworks as mentioned there, TensorFlow, MXNet, PyTorch, and so on. So that's about flexibility. When it comes to performance, we don't have enough time to digress and discuss on the various instance types that we have, but we have very powerful instance types starting from generic instance type like EC2 C5, and we recently launched C6Gs, and we also have FPGAs. And when it comes to machine learning, we also have very powerful instances that has GPUs in it, like G4s and P3DNs. So you should be able to invoke an API and instantiate these kind of very powerful instances that are meant for machine learning. And third is cost saving. On that point, I just basically want to touch on elastic inference. So from a 10,000 feet, elastic inference is the mechanism through which you can use appropriate amount of GPUs. Because we know that GPUs are super important because they are awesome when it comes to processing massively parallel algorithms, but they are very expensive. But they are needed. They are absolutely needed for training and tuning the model. And especially even when you're deploying the model in production, yes, you need GPUs in order to reduce your inference latency. But if you're just using a very powerful GPU for production, you might end up not using the whole power of the GPU instance, number one. Second, on extreme cases, that generic application may not have all the virtual CPUs that is needed. So in order to solve that conundrum, we came up with elastic inference so that when you're deploying an application into production, you can use a generic instance type like C5, and you can use the appropriate amount of GPUs. So moving to the topmost layer, which is our artificial intelligence services, we have a bunch of services that are classified under different categories. You can see, right? Vision, speech, language, chatbots, and so on. Given the time constraint, I cannot cover all the services, but the general idea is it is meant for application developers who have little to no background on deep learning and machine learning, but still they should be able to build sophisticated applications that might include ASR, NLP, NLU. The idea here is we have pre-trained services, and all you have to do from an application development perspective is invoke an endpoint using an API, and as part of the API is you send the inputs to the API, and behind the scenes the pre-trained model will do the heavy lifting and processing, and it will spit out the results. So we have recognition video, recognition image when it comes to vision, and we have a whole bunch of services when it comes to speech and language. So I just want to give a small example, right, to drive the point. I have a Ring security camera, and it alerts me when people walk into my driveway. But it's extremely useful, but sometimes it is annoying because in the middle of the night, when cats or dogs run into my driveway, I get alerted. So what I do is I go to the application, configure it so that I tell the application that, hey, inform me and send me an alert only if it is a human being. So the point here is, given a data set that consists of dogs, cats, and humans, if you want to classify between the different categories, you don't need to build a custom machine learning model. You could use a higher level artificial intelligence service like recognition video and recognition image. Now, coming to the middle layer, which is SageMaker, Amazon SageMaker is a higher level machine learning service, and the whole purpose of SageMaker is to make the job of building a custom machine learning model, building, training, tuning, and deploying a custom machine learning model as simple as possible. So let's take the same example. When somebody walks into my driveway, if I want the application to tell me whether it is my mom or my dad or my wife or my friends, then we are talking about more granular pattern, and we are talking about more specific pattern recognition. So for those cases, probably you have to build a custom machine learning model. And that's what we exactly did for this particular use case, because we were given a data set of bird sounds. It's all about birds. And the data set was thousands of audio files. But now using that, we have to classify different bird types. So that's SageMaker comes really handy. And when Raj is demonstrating, he is going to show you how you can use SageMaker as part of that, right? But from a high level, when you want to build any kind of custom machine learning model, it all has to start with the data. So you have to collect and prepare training data. So when it comes to AWS platform, obviously you all know that we have an object storage called S3. You can put all your data in S3, and SageMaker is seamlessly integrated with S3. But to begin with, you may not have all the data in S3. It might be scattered across multiple services or multiple systems. So you could use other services. That's where the beauty of the platform comes in. You can use other higher level service like Glue to go and fetch the data, extract the data, transform it, curate it, and put it in S3, right? So that is about data. And of course, SageMaker is based on Jupyter notebooks, and it is pre-built with literally 200 plus examples so that you can quickly learn from an existing example. So once you have the notebook, the data, the next step is you have to choose the right machine learning algorithm. So as we all know, we cannot digress here and talk about different kinds of algorithms, but I think Raj will be talking about a couple of them in the use case, or one of them in the use case. So the point here is SageMaker comes with 17 widely used machine learning algorithms as part of it, right? It is pre-built into it. And not only that, it is pre-built into SageMaker, a separate team in AWS is working on tweaking and fine-tuning it. Meaning that when you're using this kind of machine learning algorithms on SageMaker, you're going to get 10x performance boost. So you choose the algorithm, and the next step is you have built the model, you have to train the model, you have to tune the model, and then you have to deploy the model. So this is where it is literally one-click training, and SageMaker does all the back-end work that is needed to manage the infrastructure behind the scenes. Same thing, when you're training the model, you might have to scale your servers, you might have to scale your storage to petabytes. So if you're not using a higher level service like SageMaker, you might have to spend a lot of time in the infrastructure tasks, and it is pretty time consuming and it is pretty expensive. So when it comes to SageMaker, it abstracts all the complexities from you so that you can actually accelerate your machine learning development. So when it comes to deployment, again, it's one-click deployment. So because of the time constraint, we are not going to show, or we are not going to actually train and deploy a model, but we are going to show how you can train and deploy a model using SageMaker as part of our demo. And finally, the next step is the model is trained, it is ready to generate inferences, it's ready to generate predictions. You have to deploy it in a production environment, right? So when you do that, absolutely you have to take care of the well-architected best practices when it comes to resiliency, scalability, and security. And of course, the whole point of cloud computing platform like AWS is infrastructure as code. So you could code everything, but using SageMaker, it takes care of all the tasks for you so that you don't need to worry about auto scaling. You can just declare it. By declaring, you can say that, hey, I want to have 3 instances across multiple AZs, and so on and so forth. So it takes care of auto scaling, health checks, node failures, and security checks for you. So the whole point of SageMaker is to help you to build, train, tune, and deploy a custom machine learning model as quickly as possible. So when it comes to the benefits of SageMaker, I'm going to quickly summarize it. It is ease of use. You're going to see it as part of the demo, and I've mentioned it, one-click training and one-click deployment. And when it comes to performance, you get 10x performance because all the algorithms are optimized. The other thing that we didn't cover was SageMaker Neo. So especially in this time and age, when you're building machine learning models that might be deployed on the edge devices may not have the same powerful CPUs and memory. So when you're training a model for an edge device, you can optimize the machine learning model for that edge device considering the CPU and memory requirements and constraints. So by this way, you can achieve 2x better performance. So coming to cost, obviously you can reduce costs using SageMaker, and ground truth is part of our SageMaker platform. And ground truth is a service which automates the manual task of data labeling. So if you think about building a model, especially supervised learning, you have to annotate data, you have to label the data, which is really time consuming. So we are applying machine learning so that once we label appropriate amount of data manually, machine learning can pick up and it can automatically label the data for you. So that is ground truth. And customers are saving 70% of the cost by using ground truth. The other thing that I talked about was elastic inference when I talked about the bottommost layer. Same thing, using elastic inference, customers are saving almost 75% of the cost because of elastic inference. So these are the benefits of using SageMaker. So when I started my presentation by saying that more machine learning happens on AWS because of the broadest and deepest set of capabilities of a machine learning stack, and because of the unique differentiators that we bring to the table. And to quickly summarize the differentiators, number one, we have the broadest and deepest set of machine learning services. Second, we just don't focus on one framework like some other cloud providers. We tend to support multiple frameworks based on the feedback that we get from the customers. Third, you can really accelerate your adoption of machine learning using SageMaker. And that's what we are going to show in this particular use case. We are using SageMaker along with a couple of serverless services, and Raj will show you the architecture and discuss that. But the point here is there are a lot of case studies on how customers have saved money using SageMaker. One use case that is worth mentioning is one of the customers in the finance industry spent more than 6 months to build and deploy a machine learning model before using SageMaker, but they were able to achieve the same thing in 1 week. So the time saving and the cost saving was from 6 months to a week. That is pretty impressive. The fourth thing that I want to talk about is it is optimized for machine learning. So if you're running machine learning algorithms on SageMaker, it's going to be much efficient, much faster, and you can get at least 10x performance on the most widely used algorithms. And finally, we touched on reduced costs. So again, these are the reasons why more machine learning happens on AWS. Now, Raj is going to talk about the use case in which we use SageMaker along with a couple of other services. He's going to dive deep into the use case, talk about the pattern, talk about the customer issue, and finally, he's going to conclude it using a demo. So Raj, please take it away.
Thank you, Wilfred. You just heard from Wilfred about AWS's AI ML stack, how different parts of the stack can be used to solve a variety of problems in machine learning space. He also described to you briefly the bird classification problem using sound. So to give you some context, this project is a project funded by several organizations to study the bird diversity and their movements within Sonoma County of California. Dr. Matthew Clark is the lead principal investigator. He's a professor at Sonoma State University. So the way this project has started was they deployed a number of tiny devices that look like this. So these pouches inside of which there's a chip, and it takes a few batteries. So to show you that, this is the size of this thing. It takes three AAA batteries, and it goes in a pouch like this and gets hung up on trees in the backyards, in the forest, in the woods of the Sonoma County. And it collects a number of hours of audio depending upon the chip you put in it. And after a while, people go collect those different micro SD cards and bring them and download the data, record who recorded and where it was recorded, what was the lat long, what was the time frame, all of that. And then they proceed to go and label it using some experts. So these experts are specialists in bird sounds. They can hear the sounds and they can say if they hear a particular bird species or not. So all of that data becomes then a labeled data for machine learning process. The problem here was they had 6,000 hours of audio with very noisy data, ambient sounds, vehicles, rain, etc. Now, having all 6,000 hours of this labeled and listened to by experts is not a scalable model. So they wanted to use machine learning to be able to replicate what an expert would do or say by listening to a sound. And they were using waveforms, and they were doing a lot of research to make a machine learning model work with waveforms. And they also started using random forest classification, and it wasn't quite accurate. So, and then on top of that, a lot of this was done on local laptops. They were shipping data on hard drives, maybe sharing it on Dropboxes and things like that. Point Blue Conservation is also our partner that's part of this project. It's worth to mention that they also have very many interesting nature conservation projects along with this bird sound problem that they're working on. At AWS, we work backwards from our customers' problems. In this case, the objective was to classify bird species from sounds. They could be thousands of hours. They could be requested to be accessed by people across the country, which meant they need to have a hosted model that can scale, that is accessible from across different parts of Sonoma State University or California or the country itself, which meant they also needed to build and train these models to be accurate, to simulate a human level accuracy. And finally, they need to have a storage and computer that can scale, and it is also easy to collaborate with people from different parts of the state or the country. We decided to introduce them to deep learning models given our prior experience solving problems like this and being successful doing that. But first, we needed to bring them to understand how you can come from sound space to mel space, and then a whole suite of computer vision algorithms will become available to you to solve this problem from a classification standpoint, right? So we have a bird sound. If we could turn that into a mel spectrogram on the right hand side as you can see it, then you can use computer vision problems to classify these images as a species based on the patterns of energy you can see. So instead of saying just do this project on AWS, we wanted to show our customers that the methodology we're proposing would actually work. So I downloaded some data from xenocanter.org, in this case for 2 different species, great tit and common blackbird, used Amazon SageMaker, Keras, and did transfer learning for multi-class and binary classification. I mentioned efficient net here. We have also tried other nets, but in this particular scenario, efficient net happened to have the best recall score. So once this particular example was shown to the customer, they got really interested and decided to move forward with solving their problem on AWS with some of our proposals. The first thing we did as a part of this problem solving process was to understand how this problem should be solved in steps. So here is a 2-step process at a high level. First step is to convert the sound files into mel spectrograms. The second step is to then take the data and train machine learning models and then validate them, deploy them, and then test them in real time or with real data from the field. The first process has 6,000 hours of audio, and after several experimentations with model building and training and then inference, we came up with 1 second granularity to be the best case scenario for achieving best accuracies and being able to capture as many species as possible. Remember, in 1 minute audio that we record in forest, it can't just be one bird species. There could be multiple bird species within that same 1 minute audio in the background. So being able to capture all those different species within a 1 minute or 1 hour period where the recording happened is very important. To that effect, it requires us to generate 21 million mel spectrograms, and using AWS Fargate, our serverless container, and Lambda, our serverless compute, we were able to achieve that. Now I'll talk in a little more detail about what happens in step 1, what happens in step 2. In step 1, a file gets dropped, and the file contains a list of sound files that need to be processed. Lambda triggers and says, okay, I received a CSV file and it has a list of sound files to be processed. Fargate downloads each one of those files, processes them, puts the data back into S3 bucket. Now, what would that CSV file look like? It looks something like this. This file name, then year, month, day, hour, minute, where this recording happened, what species was found, was common name, x1, x2 represent what is the start and end in seconds of when this sound was heard, and whether there was a consensus by an expert whether it's actually present or not. So what the process does is downloads these files, uses the middle pieces as metadata to name the file, chops the 1 minute sound file. Each of these files are 1 minute in duration, from x1 to x2 with some padding, converts that into a Mel spectrogram image .png file, and puts it back into the S3 bucket. Now that data then becomes available as image files to Amazon SageMaker. In Amazon SageMaker, you can use notebooks to start experimenting. You can use training to use containers or to leverage some of the powerful instances for machine learning that we have. And finally, to deploy that model so people can make either HTTPS calls or do batch processing of multiple image files in S3 bucket. Now, I've talked about this from a theoretical standpoint. Let's look at a demo and see what this actually looks like. Here is a customer bucket that I'm allowed to show you. So what happens here is we drop a sound file or a bunch of sound files, and they will then get converted into Mel spectrograms. So the input files would look like this. They're mostly 5 megabytes. There's some experimentation on my part. And then the output looks like this. So essentially, if there's not labeled data, meaning if a full 1 minute file needs to be chopped into 1 second intervals, you'd expect to see 60 Mel spectrograms. This is the 1.5 megabyte file, so you're seeing approximately 16 of them. If I go back and show you a different one, you'll see about 60 of them. Okay, so what happens if this wasn't the file that wasn't labeled? Meaning, what happens if there's a file that has been labeled, meaning somebody listened to it and said, here are the 10 different bird species I found, and here is their X1 and X2. In that case, you only see 10 of them, and they will go into a separate folder called training folder, which we're not looking at here. Now, for the sake of this, we're going to drop a file, and we're going to go continue our demo for the rest of the process, and we'll come back and take a look to see what has happened to it during the demo. So typically, the process to wake up Lambda, wake up Fargate, spin it up, and then put the result back in here takes about 4 minutes for the very first time. Once that's kicked off, the subsequent ones go much, much faster. So while that's going on, we can go ahead and take a look at SageMaker. SageMaker, as Wilfred has talked about, has a number of functionalities. You are able to label your data that's not labeled. You have notebook instances where you can spin up notebooks, Jupyter notebooks, and start playing with them or start experimenting with models or with the data. And then you can have training jobs, whether you can directly run your training jobs in the notebooks if you have the code, or if you're using one of our containers, you could use SageMaker training, which actually spins up the training process and then shuts the instance down as soon as the training is done. And finally, we have inference. We have two different kinds. Endpoints, which are HTTPS endpoints that you can make a call to over the internet. And then second one is a batch transform job, where you point the model to a bucket where your input files are, and the model then gets spun up, make the inference, and put the results back into the same bucket. We'll take a look at all of those at a high level, but let's get started with the Jupyter Lab. Well, you can run your models on any Jupyter notebook hosted anywhere. The power of SageMaker platform is that you're able to access the most powerful GPUs and CPUs out there for machine learning. And you can run your problems on top of those instances. Number two, while you can continue of training a model completely and doing some testing on it in any notebook, without leaving that particular notebook on SageMaker, you can deploy that model to an endpoint or to a batch transform or batch prediction mode with a few lines of code, right? So here, the first line of code I would like to focus is on this one, where once I package my model after I've trained it, I can just run this line to upload my model file to a bucket on S3. If the model is on the S3 bucket with a few lines of code, I can then use execution role and SageMaker session and a couple of Keras preprocessing libraries to preprocess my input. In this case, this PNG files, which are right here, they look something like this. And I'm downloading one of them for the sake of this problem here. And we're going to go ahead and make predictions from the HTTPS endpoint. But the code to do batch predictions is right here. Batch predictions can be done on a variety of files and variety of problems where you mention the input file or your input bucket where the files are hosted. And batch predictions will go download each file, make the predictions, and write the output predictions back into the same S3 bucket to a path you specified. But for this, I've already went ahead and deployed an endpoint. I'm going to use that now to make the prediction. So that's what the predictions are. There's a 99% chance that this is a graded, 0 for graded, 1 for common blackbird. If you look at the file name itself, self-revealing, it's a graded. And then you can also run this as a REST API using our Bodo 3 client. You can just send your input as a JSON string, and you'll get a JSON string back as the output with the same exact result. We can go pick a slightly different one to make sure that this actually works. So I'll go and change the path here. In this case, it shows to be common blackbird, 99.99%, and that's where we got the file from. So in simplicity, this model for 2 classes of bird species works and is deployed as an endpoint and can be pinged by anybody if I were to give you access to it. Now let's take a look at what this looks like on the SageMaker console. So I have my models. Here are all the different models I've trained over the time I've been here at AWS, and this is the latest one we just checked out for predictions. Here's my endpoints. This particular one is the one we've just called from the notebook. If we go back to the notebook, we can see the TensorFlow inference 2020 06 09 16 45 412, and that's the same exact one here. This gives you a nice HTTPS URL that, depending on the permissions you've given to other people, they would be able to make the calls to this endpoint with their data and get predictions back. And this is especially useful if you have predictions that happen near real time, or you want to give access to ad hoc predictions for people across the whole world to be able to do this. However, if you were to have a bunch of files you collect every day or every week or every month, and you want to make predictions on them as a batch, you would do that using batch transform jobs. And then I provided the input data and the output data where I want the output to be sent to. Here I have my PNG files, and in this particular place is where the output files are sent. So for example, if you look at the input, there's a simple PNG here, and if we go one back here, here's the output with the same exact name with .out. Now what would that output file look? So essentially that looks just like that, right? So move it over. So it looks like that. So what you saw in the notebook as predictions output it will be a JSON file with the predictions in there as a JSON object. So when you have thousands of files, you will get thousands of these .out files. You will then run a process to either save this result to your database or do something with it, or maybe run other analytics on top of it, whatever is the use case dictate. So with that, I'll summarize what we just talked about. We talked about using Amazon machine learning stack for solving a bird classification problem. The input for the bird classification problem is a sound file. So we talked about how sound space can be transformed into image space using MEL spectrograms. And from a working backward standpoint, to achieve our objective of classifying bird species from sounds, and to achieve a scalable solution that is highly available, we used 4 different AWS services. S3 for collecting data, storing data, Lambda and Fargate for converting the sound files into PNG files, and SageMaker for building and training models, hosting models, and finally having more than one way to do inference from that hosted model. On top of that, a few things to note here is TensorFlow Serving Container is provided by AWS as part of the SageMaker platform. We used Keras library to train the models here, and then we also talked about being able to collaborate in terms of sharing the data or sharing the compute or being able to make predictions from any part of the world. All of those are achievable with these 4 services. If you have any questions about this, feel free to reach out to me or Wilfred. Or if you have a unique machine learning problem you're trying to solve, you can use our help. Please feel free to reach out to us and we'll be glad to help you with solving that problem. Thank you very much for the opportunity. I hope you guys stay safe in these unprecedented times and take care of yourselves and your families. Thank you.